So with part 2 on chapter 7, our idea is focusing on correlation. And with the last video, we ended with saying that the correlation coefficient is independent of the units of measure. So if units of a measure don't matter, then we are going to remove them by calculating z-scores. What better way to visualize this than to think in terms of a problem? So let me paint you a picture. In Italy, we have 135, 66 female, Italian preschool children aged 29 to 68 months. At a baseline, were used to investigate what is the best measure of adiposity, which means fat, subcutaneous fat, change in growing children. The way we measure how unhealthy or how much fat a child has is by looking at their BMI. Now that's a whole separate measurement and calculation, but roll with me for a second. BMI is measured in kilograms per meter squared. These children were recruited in Legnago, which is in Verona, Italy, in kindergarten, after excluding those with disorders affecting growth. So we don't want those affecting our normality of our data. We are looking at height and weight were measured 3 times from each child by the same trained observer at a baseline of 4 and 9 months. So this is what we have from our 135 children. Significant sample size. We get our scatter plot. We have BMI 1 versus BMI 3, both adjusted per age. What do we notice? So we have a linear, positive, moderately strong relationship. And then what can we say about its strength? So it's like moderate to strong. We see that the data is clustered at the lower end, which makes sense. And then as people go up in BMI 1, they'll tend to have a higher BMI 3, our third measurement. Well, let's actually re-look at this. Let's get rid of the units and focus on their z-scores. And by doing that, look at what happens to the x and y axes. Instead of those measurements that we had before, now we are centered at 0, cross, and 0 on the y. So if we're looking at their z-scores, we can see which data points influence our correlation score. So notice BMI z-score 3 plotted against BMI z-score 1 in our 135 subjects. This shape is still the same, isn't it? The points in quadrant 1 and quadrant 3, with either both z-scores being positive or both z-scores being negative, tend to strengthen the positive relationship because those are giving us our positive values. And the z-scores that are in quadrant 2 or quadrant 4 are opposing our relationship, and they're bringing our cumulative strength down, or they're weakening the positive relationship between z1 and z-score 3. I hope you see that. We have smaller amounts that are weakening, and we have mostly values in the first and third, giving us a positive linear association. Note, points on either axes, so either the vertical axes or the horizontal axes, have no effect on the relationship because the net effect is 0. Okay, so this gets to this whole idea of the correlation coefficient, which is our focus. The correlation coefficient gives us a numerical measurement of the strength of the linear relationship between the explanatory and response variables. It is calculated, so we say R equals the sum of the z-scores of x times the z-scores of y divided by n minus 1. Now, how did we get this, you might ask? Well, even if you mightn't, or even if you don't want to know, I'm happy to explain. Before we do, allow me to reiterate. The correlation coefficient is a numeric measurement of linearity of your data points. That means the correlation coefficient tells you how close the points come to forming or being on a line. In any discussion of correlation, you must list out the attributes mentioned earlier. So we're talking about the strength, the shape, the direction, and any outliers. You are remembering SODs. The correlation coefficient, which we call Pearson's R, is a number indicating the strength of the linear relationship of the variables. Okay, so where does this come from? Well, Pearson's R. Now for this explanation you were so eagerly awaiting. Pearson's correlation coefficient between two variables is defined as the covariance of the two variables divided by the product of their standard deviations. For a population, the formula for finding the correlation coefficient is, this is our Greek letter, again for population, which means rho is R, is the covariance of x comma y divided by sigma x times sigma y, or the standard deviation of x times the standard deviation of y. Well, what is covariance? Well, that is the expected value of x and the expected value of y multiplied together divided by their standard deviations. Obviously. And what do we notice about x minus mu? So that's the expected value of our particular data value minus, or how far away our expected value is from our mean for our x and for our y. With me so far? Great. If we expand out this idea of covariance and expected value, the previous formula defines the population correlation coefficient, represented by rho. Substituting estimates of the covariance and variances based on samples give the sample correlation coefficient, which is what R is. So look at this fun math. We could all do this and end up here. R is the sum of the z-scores of the x times the z-scores of the y divided by n minus 1. Now, do you want to do all of this fun math? I'm sure you do. This is a math class. Many of you guys are quite good at math, and that's great. So to calculate this value, we need to create several lists of data similar to the lists used finding standard deviation. So you sum up your x's, and you sum up your y's, and then you do the difference of the x minus the mean, the difference of the y values minus the mean. We would do the sum of squares for both, and then we multiply both of those sum of squares to get our correlation coefficient. Now, I really do not want you to do all that work, and I am for certain you are even less enthusiastic about doing all of that crazy amounts of work. Please don't do that to yourself. We're going to use a calculator for this. It's quite good at doing these calculations fast. So I need you to understand where this comes from and use your human minds to actually apply it. So here's the significance of this. We can always find a correlation coefficient. Given two equal-sized sets of numbers, we can create ordered pairs that will give us numbers to put into a formula to find the correlation coefficient. I mean, you could look at the length of a nose and compare it to the GPA, or you could look at someone's length of hair and compare it to IQ. Both of those are quantitative. There we can look at a correlation. So the question becomes, is that coefficient significant? Let's break that idea down even more. What do we mean by significant? Well, there's two different kinds of significance. Well, the first one is statistically significance, which this means something. And then there's socially significant, which means, like, is it relevant? So statistically significant suggests the results are due to some effect that are not a result of chance. That is what it means to be statistically significant, not due to a result of chance. Well, socially significant suggests that the results have some sort of meaning or are important and are large enough to actually matter. Do you care if you could relate hair length to IQ? No, it doesn't have any social significance, which is what we want to measure. So with significance and statistically significance of R requires some assumptions to be met. So first assumption, the variables that we are looking for are quantitative. The variables are each unimodal and symmetric. We know how to check that. We should know either from a histogram or a normal probability plot. More about that in Chapter 8. The variables do have a linear relationship. I mean, we could get an R for a collinear or curvilinear relationship, but that's not what we're looking for here. And lastly, the variables are bivariate normal, i.e., at each value of the normally distributed independent and dependent variable, they both, if I looked at the x data and looked at the y data, they both look like a normal model. So that's the significance, and that's what we mean when we say statistically significant, and that's how we can use R in its proper context. R is the correlation coefficient. So for the students' heights and weights, the correlation is 0.644. What does that mean in terms of strength? Well, we'll get to that shortly. So to test the significance of R, we must be familiar with hypothesis testing. For now, we will simply state that large values of R suggest that there is some association in the behavior of the variables together. And large values of R suggest the behavior of one variable can be suggested from the behavior of another variable. Notice, I did not claim the behavior of variable 1 is caused by variable 2. I am simply noticing changes in one variable tend to be matched by changes in another variable. With statistics, we don't state certainty. I want you to use squishy words. What do I mean by squishy words? I want approximately, tend to. We are never going to be making absolute conclusions because that's not what statistics is and that's not what real life is. So with correlation conditions, correlation, which most often we talk about Pearson's product moment correlation coefficient, that's the person that made it up, or just Pearson's R, quantifies the strength of a linear association between two quantitative variables. Before you use correlation, you must check a few things. You better be using quantitative variables, that the data is sufficiently linear, and there are no outliers. That is the outlier condition. The correlation coefficient is denoted with R for a sample and rho for a population. R rho. Looking at the conditions, let's just break those down a little bit further. So the correlation conditions. First, quantitative variable condition. Correlation applies only to quantitative variables. Period, full stop. Don't apply correlation to categorical data, masquerading itself as quantitative data. We'll see that in the table below. Check that you know the variable's units and what they measure. That is the way we check quantitative. That's how we know we are looking for R. For categorical variables, there's another correlation coefficient that's often used, and it's called Spearman's rank correlation coefficient. Think Mrs. Spearman. But that is beyond the scope of this class, so we're not going to focus on it. I bring it up, it's good to know, but you're not going to be tested on it. And what I mean when we're looking at data, if we're looking to see alcohol use versus sick days cross-tabulation, well, sick days is a measurement of time, that is quantitative, but alcohol without risk, hardly any risk, and some considerable risk, that is definitively not a quantitative variable. So for this, we would use Spearman's rank correlation coefficient and not R. We wouldn't talk about its correlation in the same way that we look at linear data. So note that. The next condition when we're looking at correlation is sufficiently linear. So you can calculate a correlation coefficient for any pair of variables. It exists. We saw that earlier when we were talking about curvilinear functions that were quadratic or possibly sinusoidal. So correlation measures the strength only of a linear association. And will be an inappropriate model if the relationship is not truly linear. So if you look at this curvilinear graph, kind of looks like a decaying exponential function, it will come up with an R. It will tell you the strength, but that does not mean that it's appropriate. So we have to check that we are sufficiently linear. And lastly, this outlier condition. Outliers can have significantly effects on our correlation coefficient. So what do I mean by that? In our first picture above, we got this little dot way up top that is pulling our line of best fit up, or having a larger, steeper slope in comparison to what generally fits our data. So it's important to note, once we have outliers, we don't just throw them away, but we note them and then we remove them from the data set to see what happens. It's possible, though unlikely, for an outlier to change a positive association into a negative correlation coefficient and vice versa. So what do I mean by that? Well, let's say we have this data set, and then we have this outlier here and this outlier over there. And because we have those two data points, it's flipping our slope. Our correlation coefficient is going to turn out to be negative. We say that that data point has leverage and is an outlier in this situation. When we include the red observations, it switches. So as usual, when you see an outlier, it's a good idea to report the correlations with and without the outliers. Maybe something important is happening there. That's why we include it initially. But maybe it doesn't help us see the trend in our overall data, and that's why we exclude it. We don't throw stuff away. So with correlation properties, the sign of a correlation coefficient gives the direction of an association. So think shape, outliers, direction, and strength. Our correlation coefficient will tell us the direction and the strength of our relationship. Correlation is always between -1 and +1. If our correlation coefficient is +1, then all of our points fit exactly on the line of best fit. But that means, exactly. If it's +1 or -1, the data falls exactly on the single straight line. And that is unlikely in the extreme. That is not going to happen. The reverse of that, a correlation coefficient near 0 indicates a weak or no association. You would expect to see that with your data just being a pure scatter plot. There's no discernible pattern. R would be 0. Continuing, correlation treats X and Y symmetrically. I would make a note of this. AP loves switching the variables and asking you what happens. Correlation of X with Y is the same as the correlation of Y with X. Now think about how we calculated R. If you remember, R is the sum of ZX times ZY all over n minus 1. Because we're multiplying those, order doesn't matter. Remember, correlation coefficient has no units. It comes from the z-scores. Correlation is not affected by changes in the center or scale of either variable because it's from z-scores. We saw that in Unit 1. Correlation can be calculated using only z-scores, and z-scores are unaffected by changes in center or scale. That is the beauty of this thing. Again, correlation measures the strength of a linear association between two variables. Notice how many times I've mentioned that fact. I want this to be in your head. Variables may have a strong association, but small Pearsons are because the association is not linear. Likewise, correlation is sensitive to outliers. Outliers have inordinately large effects on Pearson's R. Outliers tend to have large leverage. See Chapter 9 if you want to see more detail about things that are outliers and have leverage. What do I mean by a leverage? If I have this data point that's far away from my concentration of our cluster, my line is going to tend to go towards that, which means that we have leverage. And it can often make a weak association look stronger with a large R. Closing in on the end with one example on how to actually do this thing. So whenever we have a strong correlation, it is tempting to explain by claiming that the predictor variable has caused the changes in the response variable. Again, correlation is not causation. Be very careful how you express the relationship. Do not use causal language. Now, note, this says causal language, not casual, like most people are going to read that. Scatterplots and correlation coefficients never, never, never suggest causation. Why? Well, there could be hidden variables that stand behind a relationship that creates the illusion of relationships by simultaneously affecting the other two variables. We call those lurking, or oftentimes confounding, variables. We will talk more about that. For example, the number of churches in a community is strongly correlated with the high amount of criminal activity in that community. Does that mean churches cause crime? That would be insane to make that conclusion, but that's what happens when we go from correlation to causation. Now, I'm going to include this because the book includes it. I'm not a big fan of it. Some statistics books include these types of things. It's common in some fields to compute the correlations between each pair of variables in a collection of variables and arrange these correlations in a table, like so. Happiness to happiness, happiness to exercise, exercise to happiness, or sleep to exercise, or sleep to exercise to happiness. This is difficult to read. I do not personally like these correlation matrices because they imply an equal significance for each relationship that is most likely not justified. So I show it to you, but I don't want you to use something like this. Now, with always, we like to point out these common mistakes before we wrap up these chapters. First, don't say correlation when you mean association. More often than not, people say correlation when they mean association. This happens on the news countless times. The word correlation means something statistically and should be reserved for measuring the strength and direction of a linear relationship between two quantitative variables. We often run into that kind of error when two variables are said to be correlated, when they actually mean dependent. So be careful with your words because words matter. Don't correlate categorical variables. Don't do it. Use a different statistic. So that's Spearman's rank correlation coefficient. Again, beyond the scope of this course. Lastly, be sure the association is linear. There may be a strong association between two variables that have a nonlinear association. So check the conditions that I provided you. Likewise, don't assume the relationship is linear just because the correlation coefficient is high. Okay, look, here, there's a correlation of 0.979, but you notice that this data is definitely curvilinear. Also, treat outliers with respect. That's why we do shape, outliers, direction, strength. A single outlier can have leverage and can dominate the correlation coefficient. So this guy way out there is going to make all of our data fit to it. Okay. We will report out more about that later, but it's worth seeing now in this general overview. Now, I suppose you'd like to use the calculator to do all of the work for you. So to find the correlation coefficient on your TI-84s and to have prepare the calculator to report out R. If you are on a TI-84, you first need to do this thing. I need you to hit second 0 and go down to diagnostic and turn it on. Follow these instructions in the notes. If you use a TI Inspire, you don't have to do that. So let's try one example. I'm going to walk you through on the TI Inspire, and then if you have a TI-84, we can fix that in class. So I'm just going to switch over to my graphing calculator. So now that I'm on my graphing calculator, I'm going to add a list and spreadsheet. What we're looking at is the year, and then we're looking at life expectancy. So life expect. It has to be one word in order for this to do it appropriately. Again, if I'm following along with my notes, I'm just going to take the year that we have and chop off the 1900 part of it, just so the numbers are easy to visualize. So if I go 20, 30, 40, 50, 60, 70, 80, 90, and 104 years ago, and then our life expectancy in years is first one, 54.1, then 59.7, then 62.9, then 68.2, then 69.7, 70.8, 73.7, 75.4, and 77.0. I have my data typed in to my calculator. Wonderful. If you're on your TI-84, we're going to type each of these into 2 different lists, and then we're going to move on to the next part. So if we want to make a scatter plot, on your TI-84, you're going to hit second plot, and then turn on the scatter plot. Again, follow the instructions. We're going to select L1 and L2 for our X list and Y list, and then I want you to hit second mode to quit out, and hit zoom 9, and you will visualize. For us on a TI Inspire, we're going to hit Control Doc to make a new document. We're going to do data and statistics. Now year, and then life expectancy. If I do, I get my linear relationship. Now, if I wanted to actually look at this, I see that it is linear, positive. So a positive, linear, moderately strong association. What is our correlation coefficient? How can I figure that out? If I'm on my scatter plot, I would hit Menu, and now I can go down to Analyze. What I want to do is a regression model, and now my first 2 are linear mx plus b or a plus bx. We're going to stick with mx plus b for now, although many statisticians use a plus bx. We'll talk about that in class. When I type that in, I get 0.2715x plus 51.65. So that means my y-intercept, my life expectancy in year 0, so 1900, would be 51.65 years. And each year, we increase life expectancy by about 0.27 years. Pretty interesting. Now, it doesn't give me my R value. So what do I have to do if I go back to my first part, my spreadsheet? How can I do that same linear regression? If I hit Menu, and I go down to Statistics, I want to do Stat Calculations, and now I'm going to select my linear regression. I'm going to select my X is years, my Y is life expectancy, and then I don't have to mess with anything else. I'm going to hit OK, and I can see I have my slope 0.2715. I have my y-intercept 51.65. We've now got our r squared value. Interesting. And then right below that is my r of 0.97306. So the question is, what is this telling us? Well, that is telling us that we have a very strong positive linear relationship, a linear association between year and life expectancy. So I hope this was helpful for you guys. I know we are going to try to do our best to practice this in our class. Follow the schedule that I've posted for you guys in terms of when you should be completing things, and you will most likely be successful. As always, if you have questions, post them in the discussion board that's marked Unit 2. We are going to do great in the second quarter of this school year. See you in the next one, Falcons.